So welcome back, everyone. Now that we understand how MOSFETs work in terms of energy band diagrams, we can derive a few simple analytical equations to describe their IV characteristics. That's what I'd like to do in this lecture. And I'll be following an approach that is very traditional, was first developed in the 1960s, then extended in the 1970s. It does a good physical job of describing the performance of long channel transistors. Later on in the course, we'll see that this is actually a good stepping stone to understanding short channel transistors, and that's what we'll be dealing with later on in the course. Okay, so I'll point out that there are two different kinds of devices that people will describe. One is called a square law device. Now, in the square law device, the transistor characteristics will look like this. The current in the saturation region will scale as gate to source voltage minus threshold voltage squared. The first transistors that were built had very long channels, and you would often see IV characteristics that look like this. You don't see them very often these days because channel lengths are much shorter. The other type of transistor, and these are measured characteristics from a more recent transistor, would look like this. The difference is that if you look in the saturation regime, and as you increase the gate voltage, you can see that the drain current increases linearly, not quadratically, with the gate voltage minus threshold voltage squared. Now, a device like this is called a velocity saturated MOSFET because that's generally how these IV characteristics were explained in terms of something called velocity saturation. And we'll talk about what that means in just a minute or two. So we'd like to derive a few simple equations that describe the IV characteristics of both long and short velocity saturated MOSFETs. Okay, so our goal is to analyze the IV characteristics. We're actually going to do something simpler. It's easier, actually quite easy, to describe expressions for the IV characteristics in the small drain to source voltage regime, the linear regime, where we operate as a voltage controlled resistor, and to develop simple equations that describe the operation in the saturated regime with large drain to source voltages. And it actually takes quite a bit of work to connect the two smoothly. We'll talk about that in the next lecture. So let's focus on doing this. The first thing we'll do is to examine the linear regime, and the second thing we'll do is to examine the saturation regime. Okay, so just to remind you of what a MOSFET looks like in terms of energy band diagrams, this is our equilibrium energy band diagram, conduction band versus position. If we apply a large voltage to the gate over the threshold voltage, we push this barrier way down. Now electrons can get into the channel. We now have electrons in the channel of this MOSFET because they can flow in over that small energy barrier. We are going to describe the charge in there very simply, and we'll discuss in the next unit where this expression comes from. But you remember that the definition of capacitance comes from charge is equal to capacitance times voltage. It's a negative charge because these are electrons, so that's what the negative sign is doing here. The capacitance is the capacitance of this oxide layer, but it's not the total voltage. We only have charge flowing into the channel when the barrier has been pushed down far enough, when the voltage is above a critical value and the charge can flow over the barriers and into the channel. So the voltage is Vg minus that critical voltage. All right, so this should look plausible to you. We'll talk a lot more in the next unit about where that comes. That's a topic of we call MOS electrostatics. Okay. All right, so now let's look at the device where we have a high gate voltage, we're above threshold, but we have a very low drain voltage. We saw that when we did an energy band diagram, in this case, we pulled the Fermi level down in the drain. So now we call it a quasi-Fermi level because we're out of equilibrium. We pulled everything down so that we had a small slope of the energy band diagram in the channel. That means we have a negative electric field in the channel because we have a negative slope. Okay? And that negative electric field is simply the voltage between the drain and the source divided by the length of the channel. All right. We also know the charge by that simple relation, capacitance times Vg minus Vt. All right. So we remember current is charge per unit time. Okay. Another way to write that is current is charge times velocity. Moving charge gives us current. And if you go ahead and check out the dimensions here, the width of the transistor, current is proportional to the width. If we double the width, we double the current. The charge is in coulombs per unit area. The velocity is in meters per second. If you check that out, you can see that we've got the right units. Current is coulombs per second. So we have an expression for the charge. We're going to assume that the charge is 0 if the voltage is, gate voltage is below threshold. The charge is Cox Vg minus Vt above threshold, and it's got a negative sign because it's electrons. And this oxide capacitance is just the oxide, the relative dielectric constant of the oxide times epsilon naught divided by the thickness of the oxide. So this is some MOS electrostatics that we will talk about in much more detail in the next unit. All right, so with that, we've got enough that we can derive the IV characteristics in the linear regime. So our current is minus width times charge times velocity. The charge is Cox Vg minus Vt. Velocity, you'll remember that when we have an electric field, we have a drift current. It pushes electrons along at a velocity that is proportional to the electric field. The constant of proportionality is the electron mobility, a material-dependent property. So the average velocity is mobility times electric field. And the electric field is just the voltage across the channel, which is VDS, divided by the length of the channel. The units are volts per meter. So we put it all together, and we have a simple expression for the current in the linear regime. The current is W over L, the width of the transistor divided by the length of the transistor, times mobility, which tells us how fast the electrons flow in an electric field, times the capacitance of this oxide layer in farads per meter squared, times Vg minus Vt, and then times VDS. This is a very simple expression. It actually works really well, even for modern transistors, as we will see. And it's quite easy to derive and to see where it comes from. All right, so we've done the first part of our task. We've derived the IV characteristics in the linear regime. We'd like to derive the IV characteristics in the saturated regime as well. But first, let me just say a quick word about the mobility. You know, the mobility of electrons in a MOSFET is sometimes called an effective mobility. It's not the same as the mobility you would measure in a large bulk chunk of silicon, for example. Pure undoped silicon might have a mobility of 1,360 centimeters squared per volt second, for example. If we were to make a MOSFET, and we can make them in certain particular ways out of undoped silicon, we would not find a mobility of 1,360. It would be far lower, you know, closer to 200 and 300. And that's because these electrons are flowing very near the surface. The surface of this channel has roughness. The roughness can scatter and make it difficult for the electrons to flow, and that's reflected, that surface roughness scattering is reflected in a significantly lower mobility when the electrons are in the channel of a MOSFET. So that's something that you should be aware of. All right, we've done the first part. We've derived the IV characteristics in the linear regime. We now want to look in the saturated regime. And here it turns out that we need to do it two different ways. If we do it one way, we'll describe the IV characteristics of a square law device. If we do it a different way, we'll describe the IV characteristics of the velocity saturated device, the one that goes linearly. The current increases linearly with VGS minus VT. All right, so let's look at our energy band diagram. But this time we'll look at the energy band diagram where we've applied a large voltage to the drain. We pulled the energy in the drain way down. But we still have a barrier at the source that electrons have to hop over. Once they get over that barrier, it's easy for them to get out the transistor. Okay, we're going to consider that our beginning of the channel is at the top of this energy barrier. That'll be our x equals 0. And we're going to assume that the charge at that point is the same as it was under low bias, Cox Vg minus Vt. In fact, when we talk about MOS electrostatics, we'll explain that this is really the goal of the device designer, to work very hard to make sure that at this point at the top of the energy barrier, that this simple relation between the charge and the capacitance and the gate voltage still applies. That point we're going to call the virtual source, and it's going to play a very important role in our thinking about transistors and in our development of models for transistors. The virtual source is a point where we know what the charge density is because it's in a well-designed transistor. It obeys this very simple expression. Okay, now let's look at how the charge varies along the channel, right? We know the charge at the beginning of the channel, but as we march down the channel, you know, the drain voltage is large because we're in a saturated regime. The voltage gets bigger and bigger in the silicon. There's a smaller and smaller difference between the gate voltage and the voltage on the underlying silicon. That means that we're going to induce less and less charge. We have to modify our charge versus our charge relation to account for the fact that we have different amounts of charge at different points in the channel because we have a different voltage. The voltage is 0 at the virtual source at the beginning, but it gets bigger and bigger, so the charge gets smaller and smaller as we go towards the drain. Okay. Now, if we go into the saturation region, we can actually get to a point where the voltage reaches VGS minus VT. If it reaches that point, I have no charge in the channel. Well, that's interesting. You might ask, what happens? How can current flow if you have no charge in the channel? Well, it's not exactly 0. It's close to 0. It's very small. And it means in order to carry the current, the charge has to be moving very fast. To get the same current, it has to be moving much more quickly than back here, where there's a lot of charge to carry the same current. So the electric field is going to be very high in this region where we say the channel is pinched off. There's no longer a significant concentration of electrons. And that's going to help the electrons go very fast. Now, sometimes this is a point that causes confusion and difficulty in understanding how can the current continue to flow when the charge goes to 0. It's much easier to see on an energy band diagram. If we look on an energy band diagram for a long channel transistor, we will see that we'll get to a point near the end of the channel where suddenly the slope gets very steep. That's the electric field being very high in this pinch-off region. There aren't very many electrons at that region, but once they come to that region, they don't stop flowing. They just go down in potential energy and zip right out the drain. So that doesn't stop the current from flowing. We just have a very small concentration of electrons there. This dashed line shows what the potential profile would look like in a much shorter channel length transistor. You wouldn't have this region where you can obviously see pinch-off. Pinch-off like this is something that you see in a long channel transistor, and we will see that that leads to the quadratic IV characteristic. Okay, so we're trying to understand the IV characteristics of this square law device. We know that at the end of the channel, at the end of the part of the channel that has charge in it, the voltage is Vg minus Vt. We've just deduced that's what puts the charge to approximately 0. So current is still width times charge times velocity. So since the charge varies everywhere and the potential varies everywhere, but the current is constant. The current is the same everywhere. It has to be continuous, as long as there's no recombination generation going on. So we might as well pick a location that makes it easiest for us to compute the current. The location that we will pick is x equals 0 at the beginning of the channel at the virtual source. The reason we're going to pick that is because we know the charge at that point. Okay, the charge at that point is just minus Cox Vg minus Vt. Okay, that makes life easy. Now, what's the velocity at that point? We need to know the velocity too. Well, that's mobility times the electric field at that point. What's the electric field at that point? Well, it might have a complicated spatial dependence. It might be nonlinear. Under low bias, it was just VDS minus VDS divided by channel length. Now, under high bias, we know that the voltage across the channel is not VD, but it's VGS minus VT. The rest of the voltage is dropped across the pinch-off region that we're not explicitly treating. So we would guess that the electric field is about VG minus VT divided by the length of the channel, right? A little bit less than the length of the channel because a little piece of the channel is pinched off. Well, that's not bad. That's very close, but we missed it by a factor of 2. Because the electric field versus position is nonlinear, the electric field at the beginning of the channel is actually 1/2 of what we just estimated with that very simple estimate. We will actually derive that later on, but I'll just state that as a fact here. So what we can see is that the charge goes as VGS minus VT. The electric field in the channel goes as VGS minus VT. So when we put the two together, the current goes as VGS minus VT squared. We have our square law device. Okay, so we've got an IV characteristic that describes the transistor in the linear regime, describes the transistor in the saturated regime. It wasn't too much work to go through and derive that. It takes a little more work if we want to do the entire IV characteristic continuously from linear to saturation, but we won't do that yet. We'll do that a little bit later. Now, if we look at modern transistors, they're not square law devices. They behave much differently. The current in the saturation regime increases linearly with VGS minus VT. You know, what's going on here? Well, we can get a hint, and this is the explanation that people came up with in the 1970s when they began to observe these characteristics. You may remember that if you measure the velocity versus electric field in a large bulk chunk of silicon, you'll get a characteristic that will look something like this. If the electric field is not too large, the velocity will be proportional to the electric field. The constant of proportionality is the mobility. But when the electric field becomes very large, we just can't keep increasing the velocity. The velocity saturates. It saturates because the electrons gain so much energy, they find more and more ways to scatter. That scattering randomizes their velocity and just makes it harder to push them any faster. It turns out that in silicon, that saturated velocity is almost exactly 10 to the 7th centimeters per second. And it's comparable in other semiconductors. In some, it's a little bit bigger, but not dramatically bigger. So that velocity saturation occurs when there's a high electric field. What's the electric field in the channel of a modern transistor? So today's transistors might have about 1 volt between the drain and the source. They might have a channel length of about 20 nanometers long. If we estimate the average electric field inside the channel, we would find that it is 500,000 volts per centimeter. That is a very high electric field. It only takes about 10,000 volts per centimeter to saturate the velocity in bulk silicon. So we're way up here. So the velocity should be saturated. So we need to derive the IV characteristics under the assumption that the velocity is saturated because the electric field is so high in the channel. Well, that turns out to be even easier because we have the same current relation. Current is proportional to charge times velocity. Charge is Cox Vg minus Vt. The velocity is just the saturated velocity, 10 to the 7th centimeters per second everywhere. Put them all together, and we get an IV characteristic. The current is width times oxide capacitance times saturated velocity times VGS minus VT to the first power. And this describes the so-called velocity saturated devices, the typical IV characteristics that we see these days and have for a long time. Okay, so that wasn't so hard to do. We have derived the IV characteristics. For modern transistors, we're going to have a linear regime where the current is proportional to W over L, mu times capacitance times Vg minus Vt times drain voltage. And we have a saturated regime where it goes as W, Cox, Vsat, Vg minus Vt. Now there's only one problem. In our best understanding of how electrons flow in these small devices comes from very detailed, sophisticated numerical simulations. These are some results that were done by the IBM group a number of years ago for a 30 nanometer channel length transistor. Today's transistors are even shorter than that. And what you can see, each point here represents an electron. You can see them streaming across almost ballistically without being impeded by any type of scattering. You can see a region here where the electric field is very rapid. The slope is very steep. You might guess that the velocity should be clamped at 10 to the 7th centimeters per second there. Okay. But we could go along this and we could average the velocity versus position, just compute the average of each of those electrons in the channel, and we would get a profile that looks like this. So the velocity is low in the source because there are lots of electrons to carry the current. The velocity pops up in the channel because we have fewer electrons to carry the same current. And it actually gets very big at the end of the channel before it drops down to a low value when we get in the drain and we have lots of electrons to carry the current again. Now, if you look carefully at this, you can see that 10 to the 7th centimeters per second is right here. There is no hint that the velocity is actually saturating. It's not clamped at 10 to the 7th in these very short structures. The reason is simply that the electrons are in and out of the channel before they have a chance to scatter very much and slow down. So velocity saturation occurs in large bulk semiconductors, in very long channel transistors. It does not occur in modern short channel transistors. Okay, so what have we done? We have developed a model for the IV characteristics of a MOSFET. We've done it in two pieces. We developed simple analytical expressions for the linear regime. This expression works for the long or short channel devices, the quadratic or the linear devices. We also developed expressions for the saturated current. This particular expression is for the velocity saturated case. We did one for the square law device as well. And it was relatively easy to do this in two pieces. These two currents intersect at a critical voltage we call VD-SAT. If we apply a drain voltage less than VD-SAT, we use the expression for the linear current. If we apply a voltage bigger than that value, we use the saturated value. Of course, what we would prefer is an expression that goes smoothly from the linear regime to the saturated regime. Okay, so just to summarize what we've done in this particular lecture, we've developed analytical expressions that describe the linear and saturation regions of a MOSFET, and we've seen that it's relatively easy to do this. We've done it in a couple of different ways. One way that we did this was to invoke the so-called velocity saturation model. This is a model that seems to describe modern short channel devices very well, reasonably well, even though we know the physics seems to be completely wrong. So this is a mystery that we're going to have to get to the bottom of, and I hope you'll stick with me in the course and we'll explain why this happens as the course develops. One other point I just want to remind you of is that it's really the energy band diagrams that explain to us how the transistor works. If you understand the manipulation of these energy barriers with the gate and drain voltages and how electrons hop over a barrier from the source and flow out the drain, then you know how the MOSFET works. It's useful then to go back and develop analytical expressions. We need them too, but the energy band diagram approach is really what gives us the physical insight. Now, in order to use a compact model for circuit simulation, it has to smoothly describe the IV characteristic at any drain to source voltage. We can't use these piecewise linear models. So that's something that we're going to need to take care of. And in fact, the next topic of discussion will show an example of how that can be done. So we'll take the very traditional square law model. We will revisit that, but we'll do it in a way that we can smoothly connect the linear to saturated regimes, and we'll show how all of that operates. And that mysterious factor of 2 that I had to insert when I developed that model, you'll see that that just naturally comes out of the derivation. So that'll be the topic of the next lecture.